Okay, I will do this question. Okay. Okay. I will do this question. Okay. So, so you have to design a low pass FIR filter. Okay? And this is the response. This is the response. H omega is equal to e to the power minus 5j omega when omega is between omega c and minus omega c and plus omega c. Okay. So if I draw the magnitude plot, okay, if I draw the magnitude, this is we call the response, okay. Actually, this is the frequency transfer function, sometimes preferred as frequency response, okay. Frequency response, okay. So I will also use the response word to this one, okay. This is the Fourier transform of impulse response. You know that, okay. So if I plot the magnitude of this H omega, okay, it is somewhat like this. If we plot the magnitude of this H omega, magnitude of this response, okay, magnitude of this response with respect to omega, H omega magnitude, okay. Actually, this is the gain, okay. This is the gain of the filter, okay. So I am so you can understand this, okay. So I will upload it, the recorded session, then you can understand how it comes, okay. This is the gain of the filter, okay. So between omega c minus omega c and plus omega c, okay. And e to the power minus 5j omega, okay. So this is a complex number, okay. So the magnitude of this complex number is 1 here, okay. So I'm plotting the magnitude. So this will be 1 like this, okay. Then between minus 5 and minus omega c, okay. Minus 5 and minus omega t, it is 0. Plus omega c and plus 5, also it is 0. Okay. So if I plot the magnitude, it is like this. Okay. So this is low pass, this is low frequency range. Okay. So this will be a low pass filter. Okay. Actually, this is ideal low pass filter. As I told you, practical realizable filters are like this. Okay. So there can be some ripple, and this slope is not sharp. Okay. So you have this kind of slope. Then again, some ripple may be there. Okay. And yesterday I told you that depend on this function also, the filter can be defined in can be categorized in many ways into another three types. Okay. Just in the recorded session, we have discussed this. Okay. So you can refer them. Okay. So anyway, now we are going to design ideal filter. Okay. So this is our response. Okay. This is our response. Okay. Now the first thing is you need to verify what is this minus omega c and plus omega c. Okay. So the frequency is given in hertz. Okay. Frequency is given in hertz. But here the frequency for the response frequency is given by omega. So you know that the relationship between omega and f, that is omega is equal to k phi f. Okay. So you can use this relation. Okay. And as I told you, this omega c is a normalized frequency. Okay. This omega c is a normalized frequency. So here you are given enough information to find that normalized frequency. Okay. So normalized frequency means the discrete time, discrete signal frequency, discrete time signal frequency. Okay. So that is come. Okay. So you know that normalized frequency will be equal to the signal frequency. Okay. Signal frequency divided by the sampling frequency. This is the normalized frequency. Okay. So here the signal cutoff frequency is 100 and sampling frequency is 10,000. Okay. So it will be 0.01. Okay, so this is the normalized frequency in this case for our filter. Okay, and you need to find omega, normalized omega C, that is 25F. So omega C is equal to 25, F is equal to 0.01. Okay, so the omega C is equal to 0.025. Okay, so this is the cutoff frequency in our case. Okay, so now we have the cutoff frequency. Okay, so now you have to find the impulse response using this H omega. Okay, so you know that if we have H omega, okay, so this H omega is normally given. Okay, the response is normally given. The frequency domain response is normally given. Okay, so we have to find the inverse Fourier transform to find the impulse response Hn. Okay, so Hn can be found using the inverse Fourier transform. So that is the definition is 1/2 into so your integration will be within 2 that means from -5 to +5. Okay, H omega e to the power j omega n d omega. Okay, d omega. Okay, so this is the definition for the inverse Fourier transform. Then you have to do this integration. Okay, so 1/2 is there. Okay, and you know that minus infinity to minus omega c, it is 0, and minus omega c to plus omega c, it is e to the power 5j omega minus. Okay, and here e to the power j omega n d omega. Okay, then plus omega c to +5, again it is 0. So you have to do this integration only. So this integration we have done several times. Okay, so it is not much difficult. So you can calculate this Hn. Okay, so that is 1/2, 1/2. Okay, and you have to do this integration. So you can write this as e to the power j omega is common, then n -5. Okay, and you integrate this. The below also you will have j n -5 because you are going to integrate this with respect to omega. Okay, so this is the integration of this one, and your limits from minus omega c to plus omega c, and you have evaluated the minus omega c and plus omega c, that is this 0.025, 0.025 and plus 0.025. This is minus omega c to plus omega c. Then you have to do this integration, evaluation. Okay, so the Hn is equal to 1/, you can get this value 25. Okay, and I think you can use the so we have derive one function for this kind of question. Okay, so you can use that function also. It is in sign terms. Okay, it is like this. Maybe you can remember that. Okay, if this is minus omega c to plus omega c, if we apply the limits, upper limits and lower limits, e to the power j omega c n minus plus minus e to the power minus j omega c n minus 5. Okay, so it is just like e to the power j theta minus e to the power minus j theta. So it will be 2j sine theta. Okay, here the sine theta will be j omega. Okay, j omega c. Sorry, j is not there. Omega c n minus 5. Okay, so yesterday we have done this. We have done this in Monday and Tuesday classes. Okay, so you already know this. Okay, and so instead of this omega c, you have to apply the limit. Okay, then this will be 2j cancel out. Okay, and 25 is also here. Okay, 25 is also here. So 2j cancel. Okay, then you will have 1/5 n minus 5 sine omega c is 0.025 n minus 5. Okay, this one. Okay, so this is the HN. Okay, so now you can apply. Okay, so here the n is not restricted. Okay, so n can be minus infinity, plus infinity, any integer. Okay, 0, 1, 2, likewise plus infinity and minus infinity, then minus 2, minus 1, 0, like this, minus infinity. Okay, so any integer, it can be any integer. Okay, so you can find this Hn. Okay, you can find this Hn. So n is not restricted. It can be minus infinity, plus infinity. Now we have to restrict this n. Okay, we have to limit this n. Okay, by applying windowing technique. Okay, so the windowing technique, we are asked to use the rectangular window first. So we know that once you conclude the Hn, you have to find the desired impulse response. So that is equal to the obtain Hn multiplied by a window function. Okay. So now we are going to use rectangular window. Okay. So you know the window function. So that is 1 if n is equal to 0 and m minus 1. Okay, m is the number of sample and 0 otherwise. This is the rectangular window. Okay, so WRN rectangular window you can calculate as 0 to m minus 1. M is 5. No, we are asked to find 5 samples. Okay, we are asked to find 5 samples only. 5 samples. So m is equal to 1. M is equal to 5. So 5 minus 1 means 4. Okay. So 0 to 4. You have the ones are there. So 1, 2, 3, 4, 5 ones there. No. 0 to 1, 2, 3, 4. 0 to 4. Okay. This is n value. This is the n value. Okay. So this is our window function. Okay, so we have concluded the window function. Now what we have to do, we have this response Hn. Now we have to multiply it by Wn. Then you can obtain the desired frequency response. Okay, desired impulse response. Okay, you have to find the desired impulse response. Okay, so now you can apply n is 0 here. Okay, when the n is 0, that is minus 5 sine 0, 0 to 5, again minus 5. So you can calculate that value using a calculator. Okay, so that value is there. Then n is equal to 1. Again, you can apply n1 here. Then you can calculate the second sample also. I'm not calculating the sample. Okay, please do it by yourself. Okay, and then you can calculate when n is equal to 2, 3, and 4. Okay, so 2, 3, and 4. Okay, so you have 5 samples. So this is your desired response. Okay, so one question is okay. Okay, this is how you find your desired response. Okay, then you are asked to use the Hamming window. Okay, so here you are using the rectangular window. That is why we represent it using R, rectangular, WR. So that is this one. Okay, so this is the most simple window type. Okay, this is the most simple window type. And there are some complicated windows are there. Okay, so you are asked to find the Hamming window. Okay, then you should know what is the Hamming window. Okay. Okay, so this is Hamming window. I mean this one. Okay, this one. Okay, so what is that one? Mm, 0.54 minus 0.46 cos 25n n minus 1. Okay, 0.54. So Hamming window, let's say that it is WH. Okay, this H implies the Hamming. Okay, it is just a notation. Don't get confused. Okay, so it is 0.54 minus 0.46 cos 0.54, 0.60 cos 25n divided by n minus 1. Cos 25n divided by n minus 1. This is the Hamming window. This is the Hamming window. And 25n m minus 1. Sorry, 25n m minus 1, 0.454, 0.46. Okay. Okay. So this is the Hamming window. Okay. So this is valid when n is between 0 and n minus 1 as in rectangular case, then 0 otherwise. Okay, 0 otherwise. Okay. So in rectangular window, what you have to do is you no need to calculate the window, okay, because alls are 1, okay, but here you have to calculate the window function WHN, okay. So you have to apply 0 here. So cos 0 will be 1, no? Yeah, cos 0 will be 1. That means 0.54, 0.46, okay? So that is, you will have 0.08. This is the 0th sample, okay? Okay. Then by you can apply 1 here, okay? So m is equal to, in this case also m is equal to 5, okay? So you have to do this until 4, okay, until 4, okay. So that means so if I write it here again, 0.54 minus 0.46 cos 25n divided by m is 5, so you will have 4 here. So if I divided this 5 by 2n, okay, so this is okay. So when n is 1, 5 by 2, cos 5 by 2 is 0, so you will have 0.54, okay. When n is 2, okay, then you have cos 5. Cos 5 is 0, so cos 5 is minus 1, no? So you can add these two, okay, then you will have 1, okay. Likewise, you can calculate the next one and next one, okay. So likewise, you have to calculate the 5 samples here, the 5 samples of the function, okay. This is the 0th one, 1, 2, 3, 4. Up to 4, you have to calculate. Up to n minus 1, you have to calculate the sample. Okay? So your samples are there. Then you have find the HN. Okay. Then you can calculate the sample also, the 5 sample here. Okay. 1, 2, 3, 4, 0, 1, 2, 3, 4, 5 samples you can calculate. Okay. So the HN is there. Okay. So HN is there, this one. So you have to apply. Okay. You have to apply n from, so here, n from 0 to 4. N from 0 to 4. Then you can calculate the HN value up to 4. Okay. So you can calculate those values. Okay, let's say that there is H1, H2, H3, H4, H5 or something. H0, H1, H2, H3, H4. Oh, okay, so this value you can calculate. Okay, then the desired response you can get by multiplying this value, because the desired response you will have multiply the impulse value with window. Okay, with window function. Okay, so in the rectangular window case, it is 1. So you will have the same value here. Okay, because when you multiply this one, all value will be same. But here in this case, if you use Hamming window, okay, if you use Hamming window, it is not same. Okay, so you have to calculate the desired response by multiplying these two. So this one should be multiplied by this sample, then you can put that one. This value 0.54 should be multiplied by this. You can have to put value. Likewise, you have to multiply and find the 5 values. 1, 2, 3, 4, 5 values. Okay. So that is how you should do the question. Okay. Okay. So you should be able to do this kind of one. Okay. So if any question you can ask, if any unclear points you can ask. Okay. So I will upload this both recorded session. Okay. Then I hope you will understand this totally. Okay. Okay. Now, another question is there. Why we are using several window like this? Several window type. Okay. Several window type. Okay. So there are many several window types as I show you and as I told you. Okay. Rectangular window, that is the most simple one. And there are some other Bartlett, Blackman, Hamming, Kaiser, Lanczos, Turkey. Likewise, there are some very complicated windows are there. Okay. So why these are important? Okay. Actually, these are important when designing FIR filter. Okay. So to evaluate this, the performance of these several windowing techniques. Okay. So you have to find the frequency response of the window. Okay. So you have to find the frequency response of the window. Frequency response of the window. That means your window function is time domain because this n is time domain. Then you have to apply Fourier transform and you have to convert this W into omega. Okay, so this is the frequency domain. Okay, for that one, you have to apply the Fourier transform. Okay, so you know that rectangular window, that is Wn is equal to e to the power, sorry, Wn is equal to Wn is equal to 1 when n is between 0 and n minus 1, then 0 otherwise. This is the rectangular window. Okay, so I ask you to find the Fourier transform of this window. Okay, Fourier transform of this window. So you can easily find the Fourier transform of this window. Okay, and the Fourier transform is obtained as okay. Actually, in Tuesday class, I have done this, and also the recorded session, as I can remember, I have done this. I think it is easy. Okay, not much difficult. Okay, so once you find the Fourier transform of this window function with rectangular window function, this kind of one you will get. Okay, this one you will get. This is you can get easily. Okay. Using that identity, maybe you can remember that Maclaurin expression, that is 1 plus a square plus a up to infinity, that is 1 over 1 minus a. Okay, so using this one, you can get this one easily. Okay, then you have to get out from this e to the power minus j omega m divided by 2. Okay, so here you will have e to the power j omega m2 because this is 1, then this one multiplied this one, this will be 1 minus e to the power minus j omega m2 because here m is there. So once you multiply, it will be j omega m. Okay, so here m by 2. Okay, so e to the power j omega m by 2 minus e to the power minus j omega m by 2 that is sine omega m by 2. You can get this one. Okay. And here also you can get out e to the power minus j omega divided by 2. Okay. Here also you can get out e to the power minus j omega divided by 2. Okay. So you will have e to the power minus j omega divided by 2, e to the power minus j omega divided by 2. So that is sine omega 2, e to the power j theta minus e to the power minus j theta, like sine omega 2. 2j is there, so 2j cancel out, and you will have e to the power j omega m minus 1 divided by 2, because you have to simplify this one. That means e to the power minus j omega, okay, m by 2 minus half. So you will have m minus 1 by 2, m by 2 minus half. So this term is there also. Okay. So you will have this. Okay. Now actually you have to plot the magnitude value. Okay. Actually, you can plot this in MATLAB. Okay. So you can code this in MATLAB very easily, exponential terms as exponential terms. Then you can define some m, and also you can define some omega also. Okay. Omega also define the omega. It is better to define from 0 to minus 5. Okay. So here the omega you can define. Okay. Omega you can define 0 to minus 5 with some small increment 0.0001 likewise. So likewise you can define the omega. Okay. Then you can code this, the W omega magnitude of W omega. Okay. Like this, 1 minus exp minus j omega m. You can apply a value. Okay. Here I think it is 31. So the big value you can put here. Then m, likewise you can code this in MATLAB very easily. Okay. Then you have to plot this m omega with respect to omega. Okay. So that is what you have to do. You have to follow these things. Okay. And here you have to write a clear all CLC. Okay. So these are the codes you have to write in MATLAB. Okay. Then you can get this function. Okay. Sorry, you have to find the absolute value. Okay. Absolute value, ABS value of this one. Okay. So absolute value you have to find. Okay. Actually, that is the magnitude response. Okay. So then once you plot the magnitude plot, you will have this kind of one. Okay. So here, so you can see that it is starting from 0. Okay. So here you can see that it's come to the minimum level in this site. Okay. Actually, this part is called the main lobe. Okay. Main lobe of the field. Okay. So this is we are using a WM function. Okay. A window function. This is we call the main lobe, and these are side lobes. Okay. So you can see that, sorry, this one. Okay. The big one is related with the M31, and the small one is related with the M61. Okay. M is equal to 31 and M is equal to 61. Okay. So you can see that when the number of sample is increasing, this main lobe will be narrower. Okay. Will be narrower. Okay. And this main lobe is directly associated with the filter. Okay. Filter. Okay. So we have to use a narrow main lobe. Okay. And this side lobe also should be minimum. Okay. So that for a design filter also, you will have the main significant main lobe, and the side lobe will not be significant. Okay. So that is the main advantage. Okay. Main things. Okay. So actually this one easily you can plot, but if you are going to plot the magnitude for others one, you have to do some complex integration. Okay. So no need to try that. Okay. So here there are some things related with. Okay. So frequency response is the Hamming window also there. Okay. So this is M31, this is M61. So you can see that the bandwidth is narrower. Okay. So this bandwidth, and you can see that the Hamming window, here you will have a flat response in this case. Okay. Flat response, and that response is also important when we are designing the FIR filter. Okay. So what I want to tell you is that, so the frequency response of the window will take several frequency response. Okay. So the main lobe and this side lobe response should be according to our design. Okay. So that is why we are using several window techniques. Okay. So I hope that that one may be enough. Okay. That's information may be enough for you in our design, in our level. Okay. And I think we have to, I just ask you to just to refer, okay, just to refer that we can represent a LTI system using this kind of difference equation. This is not the differential equation, okay, difference equation. So that means it is this equation is related with past and future sample also. Okay. For example, this yn minus k is the delayed sample, delayed output sample, and this xn minus k is delayed input sample. Okay. So the output is related with delayed output and delayed input. Okay. So in this way also we can represent a linear time invariant system. Okay. And the FIR filter can be represented like this. Okay. Yn sigma k from 0 to n minus 1 bk x n minus k. In this way we can represent a FIR filter. Okay. FIR system. Okay. So the FIR filter also can be okay here. Okay. So the FIR filter can be represented like this. Okay. And also you know that LTI system you can represent if this is xn and if this is yn. Okay. So the yn can be represent hn convolution xn. Okay. So you have to do the convolution, linear or circular convolution. Okay. So this is the convolution. Okay. This is the convolution hk x n minus k, this k from 0 to n minus 1. Okay. So this is the convolution of yn. Okay. This one. Okay. This is the convolution. And you can see that this one and this one look like same. Okay. So hk is identical to bk. Okay. hk is identical to bk. Okay. So you can get the Z transform of hk also. So it is like this. Okay. So I think this understanding is enough for us. Okay. So there are some symmetric and asymmetric conditions are discussed. I think you need these things. Okay. Okay. So these things again we can find the even parts and odd parts. Okay. So I think that is enough. Okay, for that. Okay. So what you want to mainly you should understand that how to design a FIR filter using windowing techniques. Okay. And what are the types of window we have, and what is the importance of this window, of this several window function. Okay. So that is what you want to understand. And also just keep remember that linear system can be, linear time invariant system can be represented as a difference equation as well as convolution identity. Okay. and FIR filter also can, FIR system also can be represented like that, okay? So I think that is enough, okay? For other case, okay? Uh, uh, and I think that is okay, okay? So if you have any question, you can ask now, okay? So otherwise, you can, I think now we can, we no need to do, if you have any problem, we can discuss, okay? Otherwise, we can conclude, okay? But please wait that we need to mark the attendance, okay? Please wait. Uh, I think you can mark the attendance, okay? So if you have any problem, you can ask, we can discuss, okay? So if you have any problem, please ask, okay?